Hello students, this video is on Module 5, RTOS and IDE for Embedded System Design. So next we'll know about the topics that is going to cover in this video. Under that first one, operating system basics. So in that we'll know about the kernel. So what role the kernel will play in operating system we'll know in detail. So next is we have types of operating systems. In that first one is general purpose operating system and real-time operating system. We know already about general purpose operating system. We'll concentrate more on real-time operating system. How real-time operating system plays an important role in embedded systems. We'll know in detail about this. In certain types of firmware execution or software execution is suited for embedded devices where response time for a task is not time critical. Typical examples like electronic toys and video gaming devices. So in these examples, they don't require any time critical. Here any response delay is accepted and it will not create any optional issues or potential hazards here. Whereas certain applications, they demand time critical response to any task or events, and delay in the response may becomes so tedious. For example, like flight control systems, airbag control, and anti-locking brake system for vehicles, and nuclear monitoring devices. So these are typical examples of applications or devices which demands time critical task response. How the increasing need for time critical response for tasks or any events is addressed in embedded applications, that is by assigning priority to the task and execute high priority task when the task is ready to execute, or else dynamically keep on changing the priorities of the tasks if required on a need basis, and also by schedule the execution of the tasks based on the priorities, or by switch the execution of the task when the task is waiting for an external event or a system resource, including input output device operation. So that is why the introduction of operating system based firmware execution in embedded devices can address these needs to a greater extent. So that is why we need to know about operating system basics. So next we'll know, why do we require this operating system? What is this operating system is? So operating system which acts as a bridge between user applications and the system resources through a set of system functionalities and services. Or else we can say that OS which acts as an interface between a user and a hardware. An OS is a software which performs all the basic tasks like file management, handling input and output, and controlling peripheral devices such as disk drives and printers. So that is why we can say that OS always manages the tasks or the applications whenever it needs any system resources, it makes available to these applications. So OS is always manages the system resources. So whenever the task or any applications need the system resources, it just makes it available. The primary functions of an operating system are make the system convenient to use and organize and manage the system resources efficiently and correctly. Here this figure gives you an insight into the basic components of an operating system and their interfaces with the rest of the world. Here we can see that at the center we have an operating system which acts as a bridge between the user applications and underlying hardware. So next is the kernel. The kernel is the core of the operating system and which is responsible for managing the system resources and to establish the communication among the hardware and other system services. We can say that kernel is nothing but a computer program at the core of the computer operating system with a complete control over everything in the system. You can say also kernel as an integral part of an operating system, and it is also a portion of the operating system code that is always resident in the memory. Kernel acts as an abstraction layer between the system resources and user applications, so that we can observe in the previous figure. And kernel contains a set of system libraries and services. For a general purpose OS, the kernel contains different services for handling or managing the following, like process management, primary memory management, file system management, IO system management, secondary storage management, protection systems, and interrupt handler. Process management. Process management deals with managing the process or any tasks. Process management includes setting up the memory space for the process, loading the process code into the memory space, allocating system resources, scheduling and managing the execution of the process, setting up and managing the process control block, inter-process communication and synchronization process, termination or deletion, etc. Primary memory management. So, primary memory, this term refers to volatile memory, that is a RAM where processes are loaded, and also it stores variables and shared data which is associated with each process. While the memory management unit of the kernel is responsible for keeping track of which part of the memory area is currently used by which process, and also it is responsible for allocating and deallocating the memory space on a need basis. File system management. File is a collection of related information. A file could be a program, text files, image files, Word documents, audio video files, etc. Each of these files differ in the kind of information they hold and the way in which the information is stored. The file operation is a useful service provided by the OS. The file system management services of the kernel is responsible for the creation, deletion and alteration of files, creation, deletion and alteration of directories, saving of files in the secondary storage memory, providing automatic allocation of file space based on the amount of free space available, providing a flexible naming conversion for the files. The various file system management operations are OS dependent. For example, the kernel of Microsoft DOS OS supports a specific set of file system management operations, and they are not the same as the file system operations supported by Unix kernel. IO system management. Kernel is responsible for routing the IO request coming from different user applications to the appropriate IO devices of the system. In a well-structured OS, the direct accessing of IO devices are not allowed and the access to them are provided through a set of application programming interfaces, which is exposed by the kernel. The kernel maintains a list of all IO devices of the system. This list may be available in advance at the time of building the kernel. Some kernels dynamically updates the list of available devices and as when a new device is installed. For example, Windows XP kernel which keeps the list of updated when a new plug-in play a USB device is attached to the system. The service device manager of the kernel is responsible for handling all IO device related operations. The kernel talks to the IO device through a set of low-level system calls, which are implemented in a service called device drivers. The device drivers are specific to a device or a class of devices. The device manager is responsible for loading and unloading of device drivers and also exchanging information and system specific control signals to and from the devices. Secondary storage management. The secondary storage management deals with managing the secondary storage memory devices, if any is connected to the system. Secondary memory is used as backup medium for programs and data since the main memory is volatile. In most of the systems, the secondary storage is kept in disk, that is hard disks. The secondary storage management service of kernel deals with disk storage allocation, disk scheduling, free disk space management. Protection systems. Most of the modern operating systems are designed in such a way to support multiple users with different levels of access permissions. For example, like Windows XP with user permissions like administrator, standard, restricted, etc. Protection deals with implementing the security policies to restrict the access to both user and system resources by different applications or processors or users. In multi-user supported operating system, one user may not be allowed to view or modify the whole or the portions of another user's data or profile details. In addition, some applications may be granted with permission to make use of some of the system resources. This kind of protection is provided by protection services running within the kernel. Interrupt handler. Kernel provides handler mechanism for all external or internal interrupts generated by the system. These are some of the important services offered by the kernel of an operating system. It does not mean that the kernel contains no more than components or services explained above. Depending on the type of the operating system, a kernel may contain lesser number of components or more number of components or services. In addition to the components or services listed above, many operating systems offer a number of add-on system components to the kernel. Network communication, network management, user interface graphics, timer services, error handler, database management, etc. are the examples for some components or services. Kernel exposes the interface to the various kernel applications hosted by kernel to the user applications through a set of standard application interfaces. User applications can avail these application program interfaces calls to access the various kernel applications or services. Kernel space and user space. As we have discussed in the earlier section, the applications or services are classified into two categories, namely user applications and kernel applications. The program code corresponding to the kernel applications are kept in a contiguous area of primary memory and is protected from unauthorized access by the user programs or applications. The memory space at which the kernel code is located is known as kernel space. Similarly, all the user applications are loaded to a specific area of primary memory, and this memory area is referred as user space. User space is the memory area where user applications are loaded and executed. The partitioning of memory into kernel and user space is purely operating system dependent. Some OS implements this kind of partitioning and protection, whereas some OS do not segregate the kernel and user application code storage into two separate areas. In an operating system with virtual memory support, the user applications are loaded into its corresponding virtual memory space with demand paging technique, meaning the entire code of the user application need not to be loaded to the main memory at once. Instead, the user application code is split into two different pages, and these pages are loaded into and out of the main memory area on a need basis. The act of loading the code into and out of the main memory is termed as swapping. Swapping happens between the main memory and secondary storage memory. The kernel forms the heart of the operating system. Different approaches are adopted for building an operating system kernel. Based on kernel design, kernels are classified into monolithic and microkernel. Monolithic kernel. In monolithic kernel architecture, all kernel services run in the kernel space. Here, all kernel modules run within the same memory space under a single kernel thread. The tight internal integration of kernel modules in monolithic kernel architecture allows the effective utilization of the low level features of the underlying systems. The major drawback of this monolithic kernel is that any error or failure in any one of the kernel modules, which leads to the crashing of the entire kernel application. Examples like Linux, Solaris, MS DOS kernels. Here, this figure shows the architecture representation of monolithic kernel. Microkernel. The microkernel design incorporates only the essential set of operating system services into the kernel. The rest of the operating system services are implemented in programs known as servers, which runs in the user space. This provides a highly modular design and OS neutral abstraction to the kernel. Memory management, process management, timer systems, and interrupt handlers are the essential services which forms the part of the microkernel. Examples like Mac, QNX, Minix 3 kernels. The architecture representation of microkernel, which is shown in the figure. Microkernel based design approach offers the following benefits: robustness and configurability. So, robustness is if a problem is encountered in any of the services which runs as a server application, the same can be reconfigured and restarted without the need for restarting the entire OS. Thus, this approach is highly useful for systems which demands high availability. Since the services which run as servers or running on a different memory space, the chances of corruption of kernel services are ideally zero. In configurability, any services which run as server application can be changed without the need to restart the whole system. This makes the system dynamically configurable. So next we have types of operating systems. Depending on the type of kernel and kernel services, purpose and type of computing system where the OS is deployed and the responsiveness to applications, operating systems are classified into different types like general purpose operating system and real time operating system. General purpose operating system GPOS. The operating systems which are deployed in general computing systems, that means which are used in general computing systems, are referred as general purpose operating system GPOS. The kernel of such an OS is more generalized and it contains all kinds of services required for executing general applications. General purpose operating systems are often quite non-deterministic in behavior. Their services can inject random delays into application software and may cause slow responsiveness of an application at unexpected times. GPOs are usually deployed in computing systems where deterministic behavior is not an important criteria. Personal computers desktop system is a typical example for system where GPOs are used. Windows XP, MS DOS, etc. are example for general purpose operating system. Real time operating system. Real time implies deterministic timing behavior. Deterministic means timing behavior in RTOS context. The OS services consumes only known and expected amounts of time regardless the number of services. A real-time operating system or RTOS implements policies and rules concerning time-critical allocation of the system resources. The RTOS decides which applications should run in which order and how much time needs to be allocated for each application. Predictable performance is the hallmark of well designed RTOS. This is the best achieved by the consistent applications of policies and rules. Policies guide the design of an RTOS. Rules implement those policies and resolve policy conflicts. Windows CE, QNX, VXWorks, Micro C or OS2, etc. are examples of this real time operating system. The real time kernel. The kernel of a real time operating system is referred as real time kernel. In complement to the conventional OS kernel, the real time kernel is highly specialized and it contains only the minimal set of services required for running the user applications or any tasks. The basic functions of a real time kernel are listed below. Tasks are process management, tasks are process scheduling, tasks are process synchronization, error or exception handling, memory management, interrupt handling, time management. Whatever the basic functions of a real time kernel we have discussed in the previous slide, so we'll in detail discuss each one. So under that first one we have task process management. So this task process management deals with setting up the memory space for the task, loading the task code into the memory space, allocating the system resources, setting up a task control block for the task, and task or process termination. A task control block is used for holding the information corresponding to a task. Task control block usually contains the following set of information: task ID, task that means task identification number, task state, the current state of the task. The current state might be like, for example, ready. Task type, which indicates what is the type of this task. The task can be a hard real time, or it might be a soft real time, or it might be any background task. Next is task priority. Task priority means it gives the priority. Like if the priority is 1 means for that task it gives the highest priority. Next is task context pointer. So this pointer is used for saving some context. Next is task memory pointers to the code memory, data memory, and stack memory for any task. This task memory pointer is used. Then task system resource pointers. So this pointers points to the system resources which is used in the task. So for example, like semaphores, mutex. So we'll come across these in the later topics. Then is task pointers. So this pointers to other some TCBs and other parameters. That means this is relevant to some other task parameters. The parameters and implementation of the TCB is kernel dependent. The task control block parameters vary across different kernels based on the task management implementation. Task management service utilizes the task control block of a task in the following way. Like it creates a TCB for task on creating a task, or it deletes the TCB whenever the task has been terminated or it is deleted, and it reads the TCB to get the state of the task, and it updates the TCB with the update parameters on a need basis. So whenever it is needed, it updates the TCB, and also it modifies the TCB to change the priority of the task. Next basic function of real-time kernel is task process scheduling. So this task process scheduling deals with sharing the CPU among various tasks or any processes. A kernel application is called scheduler, which handles the task scheduling. Scheduler is nothing but it's an algorithm implementation which performs the efficient and optimal scheduling of tasks to provide a deterministic behavior. So next type we have task process synchronization. So this deals with synchronizing the concurrent access of a resource which is shared across multiple tasks and the communication between various tasks. So next we have error or exception handling. So this deals with registering and handling the errors occurred or exceptions raised during the execution of tasks. Insufficient memory, timeouts, deadlocks, deadline missing, bus error, divide by zero, unknown instruction execution, etc. are examples of errors or exceptions. So we'll discuss about deadlocks and deadline missing everything in the next coming topics. So errors or exceptions can handle at the kernel level services or at the task level. Deadlock is an example for kernel level exception, whereas timeout is an example for task level exception. The OS kernel gives the information about the error in the form of system call. Watchdog timer is a mechanism for handling the timeouts for tasks. Certain tasks may involve the waiting of external events from devices. These tasks will wait infinitely when the external device is not responding, and the task will generate a hang up behavior. In order to avoid these types of scenarios, a proper timeout mechanism should be implemented. A watchdog timer is normally used in such situations. The watchdog will be loaded with the maximum expected wait time for the event, and if the wait is not triggered within this wait time, the same is informed to the task and the task is timeout. If the event happens before the timeout, the watchdog is resetted. Next is memory management. Compared to general purpose operating systems, the memory management function of a RTOS kernel is slightly different. In general, the memory allocation time increases depending on the size of the block of memory needs to be allocated and the state of the allocated memory block. Since predictable timing and deterministic behavior are the primary focus of an RTOS, it achieves this by compromising the effectiveness of memory allocation. RTOS makes use of block-based memory allocation technique instead of usual dynamic memory allocation technique used by the general purpose OS. RTOS kernel uses blocks of fixed size of dynamic memory, and the block is allocated for a task on a need basis. The blocks are stored in a free buffer queue. To achieve predictable timing and avoid the timing overheads, most of the RTOS kernels allows tasks to access any of the memory blocks without any memory protection. RTOS kernels assume that the whole design is proven correct and protection is unnecessary. Some commercial RTOS kernels allow memory protection as optional, and the kernel enters a fail-safe mode when an illegal memory access occurs. A few RTOS kernels implement virtual memory concept for memory allocation if the system supports secondary memory storage like HDD and flash memory, where HDD is hard disk drive and flash memory. In the block-based memory allocation, a block of fixed memory is always allocated for tasks on need basis and it is taken as a unit. Hence, there will not be any memory fragmentation issues. The memory allocation can be implemented as constant functions and thereby it consumes fixed amount of time for memory allocation. This leaves the deterministic behavior of the RTOS kernel untouched. The block memory concept avoids the garbage collection overhead also. The block-based memory allocation achieves deterministic behavior with the trade-off limited choice of memory chunk size and suboptimal memory usage. So chunk size is nothing but a multiple of 65,536 bytes of valid is nothing but a chunk size. And suboptimal memory usage is nothing but the optimal less than a optimal memory usage, we call it as suboptimal memory usage. So next we have interrupt handling. So this deals with the handling of various types of interrupts. Interrupts provide real time behavior to systems. Interrupts inform the processor that an external device or an associated task requires immediate attention of the CPU. Interrupts can be either synchronous or asynchronous. Interrupts which occurs in synchronous with the currently executing task is known as synchronous interrupts. Usually the software interrupts falls under this synchronous interrupt category. Divide by zero, memory segmentation errors, etc. are examples of synchronous interrupts. For synchronous interrupts, the interrupt handler runs in the same context of the interrupting task. Asynchronous interrupts are interrupts which occurs at any point of execution of any task and are not in synchronous with the currently executing task. The interrupts generated by external devices connected to the processor or any controller are time overflow interrupts, serial data reception or transmission interrupts are some of the examples of this asynchronous interrupts. For asynchronous interrupts, the interrupt handler is usually written as a separate task and it runs in a different context. Hence, a context switch happens while handling the asynchronous interrupts. Priority levels can be assigned to the interrupts and each interrupt can be enabled or disabled individually. Most of the RTOS kernel implements nested interrupts architecture. Interrupt nesting allows the preemption, that is, interruption, of an interrupt service routine servicing an interrupt by a high priority interrupt. So, next is time management. Accurate time management is essential for providing precise time reference for all applications. The time reference to kernel is provided by a high resolution real time clock hardware chip. The hardware timer is programmed to interrupt the processor or controller at a fixed rate. The timer interrupt is referred as timer tick. The timer tick is taken as the timing reference by the kernel. The timer tick interval may vary depending on hardware timer. Usually this timer tick varies in microseconds range. The time parameter for the task are expressed as the multiples of the timer tick. The system time is updated based on timer tick. If the system time register is 32 bits wide and the timer tick interval is 1 milliseconds and the system time register will reset in 2 to the power 32 into 10 microseconds. So that when it resets means if we want in terms of days, we have to divide it by 24 into 60 into 60. Then we'll get the value approximately 0.0497 days. That is equal to 1.19 hours. So if the timer tick interval is 1 millisecond, the system time register will reset in. So 1 millisecond is 2 raised to 32 multiplied by 10 raised to minus 3 seconds. So then if you want to convert it into days, divided by 24 into 60 into 60. So we'll get 49.7 days. So which is approximately 50 days. The timer tick interrupt is handled by the timer interrupt handler of kernel. The timer tick interrupt can be utilized for implementing the following actions. Save the current context, increment the system time register by 1, generating timing error and reset the system time register if the timer tick count is greater than the maximum range available for the system time register, and update the timers implemented in kernel. Next, it activates the periodic tasks which are in the idle state. It invokes the scheduler and schedule the task again based on the scheduling algorithm. It deletes all the terminated tasks and their associated data structures. Load the context for the first task in the ready queue. Due to the rescheduling, the ready task might be changed to a new one from the task which was preempted by timer interrupt task. Hard real time. Real time operating systems that strictly adhere to the timing constraints for a task is referred as hard real time systems. A hard real time system must meet the deadlines for a task without any slippage. That means without missing any deadlines, it has to complete the task. Missing any deadline may produce a harmful results for hard real-time systems, including permanent data loss and irrecoverable damages to the system or users. Hard real-time systems emphasize the principle a late answer is a wrong answer. A system can have several such tasks, and key to their correct operation lies in scheduling them so that they meet their time constraints. Airbag control systems and anti lock brake systems of vehicles are typical examples of hard real time systems. The airbag control system should be into action and deploy the airbag when the vehicle meets a severe accident. Ideally speaking, the time for triggering the airbag deployment task when an accident is sensed by the airbag control system should be zero, and the airbags should be deployed exactly within the time frame which is predefined for airbag deployment task. Any delay in the deployment of airbags makes the life of the passengers under threat. When the airbag deployment task is triggered, the currently executing task must be preempted. The airbag deployment task should be brought into execution, and the necessary IO systems should be made readily available for the airbag deployment task. To meet the strict deadline, the time between the airbag deployment event triggering and start of airbag deployment task execution should be minimum. Hard real-time systems does not implement the virtual memory model for handling the memory. This eliminates the delay in swapping in and out of the code corresponding to the task to and from the primary memory. In general, the presence of human in the loop for task introduces unexpected delay in the task execution. Most of the hard real-time systems are automatic and does not contain a human in the loop. Soft real time. Real time operating system that does not guarantee meeting deadlines but offer the best effort to meet the deadline are referred as soft real time systems. Missing deadlines for tasks are acceptable for a soft real time system if the frequency of deadline missing is within the compliance limit of the quality of service. A soft real time system emphasizes the principle a late answer is an acceptable answer, but it could have done it bit faster. Soft real time system, most of them have a human in the loop. Automatic teller machine ATM is a typical example for soft real time system. If the ATM takes a few seconds more than the ideal operation time, nothing fatal happens there. An audio video playback system is another example for soft real time system. No potential damage arises if a sample comes late by fraction of a second for playback. These are the two books referred for these topics.